Section of Chapter 4, we're going to learn about electron configurations. We finished the previous section with the quantum mechanical description of the hydrogen atom. And we saw that in the hydrogen atom, we have principal energy levels indicated by the letter N, and this shows the first four principal energy levels. Each principal energy level is divided into one or more sublevels, indicated by the designations 1s, 2s, 2p, and so forth. And each sublevel can contain up to between 1 and 7 orbitals. But what about everything else? This only applies to hydrogen. Well, there's good news and bad news. The bad news is that we cannot solve Schrödinger's equation exactly for other elements. However, other elements do have what are called hydrogen-like orbitals, meaning the same general number, size, and shape, just different energies. So, let's learn about these. To describe the arrangement of electrons in any atom, we will write what is called an electron configuration. An electron configuration is a list of which sublevels are occupied by electrons and how many electrons are in each sublevel. So the skill is as follows. I give you any element on the periodic table, and you will write its ground state electron configuration. And for that, we're going to use three tools. They are the Outbound Principle, the Pauli exclusion principle, which we talked about in the previous video, and what's known as Hund's rule. So let's begin. The Outbound Principle says an electron occupies the lowest energy orbital that can receive it. Aufbau is from the German verb bauen, which means to build up. So we build up the electron configuration of an atom by placing electrons into sublevels in order of increasing energy, starting with lowest energy and working our way up to higher energy. When a sublevel fills up with electrons, we go to the next higher energy sublevel. And when we run out of electrons, we stop because we're finished. The Pauli exclusion principle, you'll recall from section 4.2, says that no two electrons in the same orbital can have the same value of spin. The two possible values of spin are plus 1/2 and minus 1/2. So, an orbital can hold up to 2 electrons as long as they have opposite spins. Hund's rule we'll get to in a minute. So, let's begin by writing the electron configurations of hydrogen and helium. Hydrogen has 1 electron. The lowest energy sublevel that's available is the 1s sublevel, so we'll put the electron in the 1s orbital. We can represent that by drawing an orbital notation diagram, which represents the 1s orbital as a horizontal line, and the electron is represented by an arrow, which can either be pointing up or down to indicate the two possible values of spin. The electron configuration is simply 1s superscript 1, meaning there is 1 electron in the 1s sublevel. Helium has 2 electrons, and there's still room in the 1s sublevel. But the electron must have opposite spin. So for the orbital notation, I will draw the horizontal line with the 1s below to indicate the 1s orbital, and now I'll place 2 electrons in it, one with an arrow pointing up, the other represented by an arrow pointing down, to indicate that these 2 electrons have opposite spin. They are now paired, and I write the electron configuration as 1s2. Let's continue. Lithium, beryllium, and boron? Well, we simply look at the periodic table, count the number of electrons, and start placing them in the lowest energy sublevel that has room. Lithium has 3 electrons, so I'll place 2 in the 1s with opposite spins and 1 in the 2s. I'll write the configuration 1s2, 2s1. Beryllium has 4 electrons, 2 in the 1s, 2 in the 2s, and I'll write the configuration 1s2, 2s2. Boron has 5 electrons, and there's no more room in the 2s sublevel, so I'm going to have to start putting electrons in the 2p sublevel. So for boron, I'll write the configuration 1s2, 2s2, 2p1. Carbon has 6 electrons, and the question is, where does that 6th electron go in the 2p sublevel? Do I pair it up in the 2p orbital that already has 1 electron, or do I put it in an empty orbital? That's where Hund's rule comes in. Hund's rule says, when placing electrons in orbitals of equal energy, place 1 electron in each empty orbital with the same spin before placing 2 electrons in a single orbital. A simpler way of stating Hund's rule is simply maximize the number of unpaired electrons. An unpaired electron being an electron that is an orbital by itself. So, carbon has 6 electrons. I'll place 2 electrons in the 2p sublevel in separate orbitals. 1s2, 2s2, 2p2. Nitrogen has 7 electrons. 1s2, 2s2, 2p3. Oxygen has 8 electrons, 2 in the 1s sublevel, 2 in the 2s sublevel, 1, 2, 3, 4 in the 2p sublevel, 1s2, 2s2, 2p4. Let's continue across the period. Fluorine has 9 electrons. I'll place 2 in the 1s, 2 in the 2s, and 5 in the 2p sublevel. 1s2, 2s2, 2p5. Neon has 10 electrons. Hey, look, we're at the end of the second period. I wonder if that's significant. 1s2, 2s2, 2p1, 2, 3, 4, 5, 6. Wait a minute. Why did we fill the 2s sublevel before the 2p sublevel? In the hydrogen atom, the 2s and the 2p sublevel are at the same energy, as is the case in all sublevels in a given principal energy level. Well, I've got a little bit of bad news for you, and that is, once we have more than one electron in the atom, the sublevels in a given principal energy level are no longer at the same energy. In fact, they start to split. As you can see in this diagram, the 2s sublevel is below the 2p sublevel in energy, the 3s is below the 3p, which is below the 3d. The 4s actually is lower in energy than the 3d, oddly enough. So we need to know the order in which the energy levels fill for these polyelectronic atoms. Here's the actual energy level diagram for a polyelectronic atom. The order in which the sublevels fill are 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then 4p. So the question is, do you have to memorize this? The answer is no, and here is why. The coolest thing in all of chemistry that you will see this year is the following. Remember a couple of minutes ago when I said, is it a coincidence that once we reach the configuration of neon with 10 electrons and a completely filled 2p sublevel, we reach the end of the period? It is not. The shape, size, and dimensions of the periodic table are directly determined by the order in which the sublevels are filled and the number of electrons each sublevel can hold. Okay? So you don't need to memorize the energy level ordering that was on the previous page. When you're writing electron configurations, you simply use the periodic table as your guide. On the next slide, I have a very, very important diagram that you want to make sure that you keep handy. And this shows that regions of the periodic table correspond to filling specific sublevels. Check this out. Okay? In each stretch of elements, I've labeled this as corresponding to filling a particular sublevel. So in going from lithium to beryllium, we're filling the 2s sublevel. On going from boron to neon, we're filling the 2p sublevel, and so forth. So when you're writing an electron configuration, take out your periodic table, identify the element on the periodic table, and then simply start with 1s. Let's do some examples. Here are some third period elements. Magnesium, 1s2, 2s2, 2p6, 3s2. Notice that after I fill the 2p sublevel at neon, the next electrons go into the 3s sublevel. I need 2 of them to get to magnesium, so I finish with 3s2. For silicon, 1s2, 2s2, 2p6, 3s2. After 3s comes the 3p sublevel, and as you can see, I need 2 electrons in the 3p sublevel to get to silicon, so I'll finish with 3p2. Chlorine, if you look at the periodic table, you'll see has 5 electrons in the 2p sublevel. So I'll write the configuration 1s2. Oops, sorry, let me fix that. 1s2, 2s2, 2p6, 3s2, 3p5. In the fourth period, let's go back and look. At the end of the third period, with 18 electrons, I've completed the configuration of argon. The next electrons go into the 4s sublevel at the beginning of the fourth period. So for calcium, I'll place 2 electrons in the 4s sublevel. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. For iron, now notice, after calcium, with 20 electrons, I filled the 4s sublevel, but now remember the 3d sublevel actually fills after the 4s sublevel. So even though I'm in the fourth period, after filling the 4s sublevel, we begin to place electrons in the 3d sublevel. So for iron, I'll write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and to get to iron, I need 6 electrons in the 3d sublevel, so I'll finish it with 3d6. Let's do one more. For selenium, I filled the 3d sublevel, and now I'm going to place 4 electrons in the 4p sublevel. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4, and as you can see, this is starting to get really, really tedious, okay? What happens when we get to really heavy elements? Well, scientists have come up with a way to simplify this, and it is called the noble gas abbreviation. It is permissible to show the electron configuration that represents the previous noble gas, meaning the noble gas that achieved its configuration before the element whose configuration you're writing, by simply placing the symbol of the noble gas in square brackets. The noble gas that comes before selenium is argon. That corresponds to 18 electrons up to and including the 3p sublevel. So I will take these first 18 electrons and simply represent them by placing argon in square brackets. You can only do this with noble gases, by the way. To complete the configuration, I'll list the sublevels that are filled after that. So the correct configuration for selenium would be argon, 4s2, 3d10, 4p4. And as far as I'm concerned, you can always use the noble gas abbreviation. What about barium? Well, barium's got 56 electrons. I'm not going to start at 1s2, 2s2, and so forth. That would just take way too long. So I look at the periodic table and I go backwards and I see that the noble gas before barium is xenon. So I'll represent the first 54 electrons in barium by putting the symbol of xenon in square brackets. The sublevel that fills after xenon, let me go back and check, is the 6s sublevel. So barium has 2 electrons in the 6s sublevel. The configuration is xenon 6s2. After barium is lanthanum. And for lanthanum, I will place the next electron in the 5d sublevel, xenon 6s2, 5d1. After lanthanum, atomic number 57, is cerium, atomic number 58, and something a little crazy happens, which is, look on the chart, we jump down to the rare earth elements, specifically the lanthanide series. Remember, we said the lanthanides are the elements following lanthanum, and we see that with cerium, we begin placing electrons in the 4f sublevel. Yes, it's a little bit confusing, but simply follow the sequence of atomic numbers on the periodic table, 55, 56, 57, 58. You can clearly see you begin to fill the 4f sublevel. So cerium has the configuration xenon, 6s2, 5d1, 4f1, and as I progress across the lanthanide series, I'll successfully place electrons in the 4f sublevel until, with lutetium, atomic number 71, the 4f sublevel is completely filled. I will write the configuration xenon, 6s2, 4f14, 5d1. Remember, we still have that one electron hanging out by itself in the 5d sublevel. Now, you may ask, does the order in which you list the sublevels matter? In my book, it doesn't. As long as you have the correct sublevels with the correct number of electrons in each, it doesn't matter the order in which you list them. My preference is to list them in the order in which they fill. So for lutetium, because the 4f sublevel fills before the 5d, I list it in this way. After lutetium, now, atomic number 71, we go to hafnium, atomic number 72. And as you can see, now we're back in the 6th period. So I'll write the configuration of hafnium as xenon, 6s2, 4f14, 5d2, and I'll continue along filling the 5d sublevel until I've completely filled it with 10 electrons, which corresponds to mercury. So mercury has the configuration xenon, 6s2, 4f14, 5d10. We'll do more examples of these in class. Now, finally, what are unpaired electrons? Well, as we said before, they're electrons that are present in singly occupied orbitals, meaning that they're not paired with another electron with opposite spin in the same orbital. One of the things you can use an electron configuration for is to determine how many unpaired electrons are present in an atom. Let's take vanadium, for example. The configuration of vanadium is argon, 4s2, 3d3. Simply looking at that configuration doesn't necessarily tell you that there are 3 unpaired electrons. What you have to draw is what's called a partial orbital notation diagram, which shows only partially filled sublevels, which in this case is the 3d. 1, 2, 3. Following Kuhn's rule, we place each of the 3 electrons into a separate orbital with the same spin, so we see that vanadium has 3 unpaired electrons. I can ask another question, and that is, how many 4th period elements have exactly 2 unpaired electrons? Well, if vanadium has 3 unpaired electrons, then we would predict that the element before it, titanium, would have only 2 unpaired electrons. Titanium has the configuration argon, 4s2, 3d2. And if I draw a partial orbital notation diagram to indicate the 3d sublevel, I will see that I have 2 unpaired electrons. Are there any other elements in the 4th period that can also have exactly 2 unpaired electrons? Titanium has 2 because it has 2 singly occupied orbitals and 3 empty orbitals in the 3d sublevel. But what if I had 2 singly occupied orbitals and 3 completely filled orbitals? In other words, 8 electrons in the 3d sublevel. That would also give me exactly 2 unpaired electrons. Which element has 8 electrons in the 3d sublevel? Pause, look at the periodic table, and you will see it is nickel. Nickel has the configuration argon, 4s2, 3d8. And if I draw a partial orbital notation diagram for the 3d sublevel and place 8 electrons in it, 1, 2, 3, 4, 5, 6, 7, 8. I see I also have 2 unpaired electrons. But we're not finished, because in the 4th period we also have the 4p sublevel, which could have 2 unpaired electrons in it. And if I look on the periodic table and see which element has 2 electrons in the 4p sublevel, I see that's germanium. Germanium has the configuration argon, 4s2, 3d10, 4p2. Now my partial orbital notation diagram will include only the 4p sublevel, because that's the only partially filled sublevel. I'll place 2 electrons in it. And as before, there's another possibility, namely the one in which the 4p sublevel has 4 electrons in it, so that there are 2 singly occupied orbitals and 1 filled orbital. That would correspond to selenium, as we saw before, argon, 4s2, 3d10, 4p4, with 4 electrons in the 4p sublevel, 1, 2, 3, 4. So we see in the 4th period, there are actually 4 elements that have exactly 2 unpaired electrons. Our final topic, what is an excited state electron configuration? Up until now, all the electron configurations we've written have corresponded to the ground state, meaning that all of the electrons are in the lowest energy sublevels that can accommodate them, consistent with the Aufbau principle. An excited state configuration is an electron configuration in which one or more electrons is not in the lowest energy sublevel that has room for it. So here's a question for you. Which of the following electron configurations represents an excited state? All you're doing is looking at the electron configuration I provide you and asking yourself, are these sublevels filling in the correct order as determined by the periodic table? 1s2, 2s2, 2p5. That looks good to me. In fact, we can tell simply by the number of electrons that has to be fluorine. 1s2, 2s2, 2p6, 3s2, 3p5, 4s1. No. Placing an electron in the 4s sublevel before the 3p is filled with 6 electrons does not correspond to the ground state. I can tell that what it actually should be is 1s2, 2s2, 2p6, 3s2, 3p6, and you can tell from the periodic table that completely filling the 3p sublevel corresponds to argon. 1s2, 2s2, 2p6, 3s2, 3p5, 4s2, 3d5, 4p6. Nah, you've got a partially filled 3p sublevel, a partially filled 3d sublevel, and electrons after that. That's not the ground state. To identify the element, I'm going to make my life a whole lot easier and simply count the total number of electrons shown there. If you add up the subscripts in that electron configuration, you'll see they total 30. And when you look on the periodic table, you'll see the element that has 30 electrons is zinc. So to write the ground state configuration of a zinc atom, I'm going to use the noble gas abbreviation to make my life easier. argon, 4s2, 3d10. There are 30 electrons right there. So what you should be able to do is, if I give you an electron configuration, tell me whether it represents an excited state of the element or the ground state. If it is an excited state electron configuration, rewrite it to represent the ground state, as I did in the second and third examples, and then identify the element simply by counting up the electrons. That's pretty much it on electron configurations.